has different speeds.
Okay. I mean, yeah, great. Just you make it more complicated if you want. Put a PID controller on there. I don't. You can go all the way if you want, but just a fan on its own, I only get so excited.
We'll make it exciting.
There we go. Put a picture on it that spirals. Ooh.
There you go. Some like rainbow LED.
No, that's what I was gonna say.
Just make it green.
All right, let's see. Okay, let's get started. Last time we were talking about analog to digital converters. So these are like a fundamental core element of microcontrollers. Not all of them have them. Most do, because generally you're going to want to interact with the physical world around you, and the physical world is analog. So we talked about two types. We talked about maybe three. We talked about flash ADC. So that was the one where it's a resistor chain, ladder of resistor values, and then so it generates voltages, reference voltages, and you're just comparing. Is my voltage higher or lower than this reference voltage? And you just need a resistor for basically every step you make. Then we talked about slope integrator and the corollary to that, the dual slope integrator. Slope integrator is basically, let's use time. Remember, your computing systems are only good at measuring time. That's about the only physical property they can do well. But this is great because now if you have a nice calibrated current source, you can go and measure the passage of time until some threshold eats some other threshold, and boom, you can get an ADC value that's proportional to the time it took to ramp up to that threshold value. Does anybody remember the trade-offs of what was good or bad about flash ADCs? How about one good thing, one bad thing? It's fast, yep. You got it right in the name, telling us it's a flash ADC, fantastic. What's the bad thing about it? Space. If you want more resolution, you have to give up more space. So resistors are large on silicon. For the slope integrator, what's one pro and one con? Are you sitting? You got me confused. You're sitting up there now? No, but it's fine. Okay. Sorry, what was it?
They don't take up the space at all. They scale really well.
Yeah. Comparators are power. They consume a lot of power. You only have one comparator. You need some fancy analog, current source. That's fine. Those things are all relatively small. So yeah, it's small. What's another good thing about it?
You can set the precision up really high.
Yep.
For very little cost.
Yep, you can get the precision high. It really comes down to not your ability to measure time, because you can imagine you can go very, very fast and make lots of little steps in there and get high precision. But it comes down to the quality of your analog things, right? Is there inherent noise? Is your current source accurate enough to give you the measurement? That's what a slope integrator is good for. While the flash is you have to have lots and lots of small resistors. That's the downside. What's the bad thing about slope integrator? Yeah. They're slow, right? That's the trade-off. Okay, so now we're going to go and try and find a happy balance between the two of them. There are many types of ADC architectures. Oh, those integrated circuit designers want to keep making them up. And PhD theses are being written about them. But then we also have the standard ones that work every day, or solve the general case problem. So this is one of those examples. It's called a successive approximation ADC, or SAR. I always have to remember every year what SAR stands for after 20 years of using them. I forget what they actually stand for. So it's overly complicated, but there's an advantage, okay? And so the idea here is that you are going to have some input voltage that comes in, and you're going to compare it to some reference value. So just like the flash ADC, but the flash ADC was too large. So instead of inherently using that ladder structure, we'll use a DAC, a digital analog converter. We haven't introduced that concept, what those things are yet. We're going to do that in 30 minutes or so. So for right now, assume this black box is okay. Don't freak out because you don't know how this black box works. Just assume that we could make a digital analog converter that's relatively small compared to what you would need with a resistor ladder, okay? Does that make sense? So what we're going to do is we're going to compare, through this complicated network, we're going to compare some input voltage to some reference voltage, and we're going to dynamically change that reference voltage to search. Basically, there's a little search algorithm in that control thing, very simple, binary search. And it's going to say, okay, I have an incoming value. Am I higher or lower than it? And then, okay, well, I'm here. The value's higher than me. Then I'm going to go 50%, 50%, kind of walk myself to that value. So it's a way to successively search for your analog value. And I'll show you a false stat. But at this moment, does anybody have any questions? You should probably be confused, but I can ask any questions, answer questions. Okay. This is an example of how the binary search would work. So you have some reference voltage here. So remember, we have the sample and hold stage on your ADCs in your lab kit or on your dev kit. They're going to have a sample and hold time or a sample time where they say it's going to take this many clock cycles to sample a value, and you can't go faster than that. So here they're showing a sample, kind of assuming that you start at 0 and you're going to ramp up until some threshold value, and you're going to say, let's assume that the drive strength of the analog signal coming in is fast enough so it comes to some steady state before my sample time is up. Some assumptions can be made. You can adjust your sample time in your dev kits if you needed to. Okay, so say we have some value here that you're going to say, oh, okay, it's sampled, it's held, and see it's holding that value so that we can apply the successive approximation search algorithm here to find that value. So this is where that sample and hold circuit comes in. We're holding it here. Then we're going to say something like, okay, we're going to try a value, like 50% of my VREF 0 or VREF negative to VREF positive. So let's go at the 50% point, search, and then you do a comparison. Are you higher or lower than that? So at this time frame, right, the analog value is higher than this, and how are we making that decision, whether it's higher or lower? Comparator, exactly, we're using this comparator, and then you say, okay, it's higher. Well, then I'm going to jump up to a binary search. I'm going to increment this binary value that represents that analog voltage. We're going to increment that by 1 decimal place, so we're going to go binary place, go up to there at 110. We find that that's higher, okay, then we're going to go down to lower, higher, and we're going to try and converge on some particular value. Okay? You're either all very excited about that, which I can understand, makes perfect sense, or you're like, I don't understand any of that. So in this case, we have some sample and hold. So sample time, conversion time. Conversion time is in some ways non-deterministic. Well, that's not true. You don't know beforehand if you're going to converge quickly or slowly. If it happens to be the worst possible choice for a binary search, it could take you your entire bit length to get there. So if you had 16-bit ADC, it might take you all 16 steps to find that value. Or you could guess it like on the second try. You don't know, right? So that's, in that case, the hardware engineers, basically say, we're just going to guarantee it's going to take 16 cycles. We're not going to try and go for the shortest, fastest time, just in case we lucked into the value. We're going to go for the longest period of time, just for safety. I guess somebody probably figures out how to make it faster. That's great. Okay. This is just another example of showing how you could do a binary search as a function of time if you had like a time varying signal. Basically, you sample, you do a conversion to some value, then you sample again, conversion. And so the output here is going to be some binary value. That's just represented there. All right, so let's see how it works. Oh, yes, okay. Showing that you're going to step through the search algorithm to find the value. Okay. Yeah, it doesn't work. All right, so in this simulation, we have an input. Input's here. This is what we're comparing to, the output of the comparator. So we have This is our DAC, so it's a digital analog converter. Again, we haven't talked about how that works. We're just going to assume for right now that it is smaller than an alternative, like a large resistor ladder. So we're trying to save some space. Okay, so that's going to put an analog voltage out here. I have basically an on switch. This thing will turn on the conversion process. There's a timer that's going to walk us through that conversion process. A little controller I built. You can actually code very simple things like essentially Verilog in Falstad. So I made a little controller, and then that controls the DAC to kind of do the searching. All right, so here we go. As you can see, as I move this value around here, I can just arbitrarily choose an analog value. And already you see that the comparator was just switching before I even turned on the device, right? It's already making a decision for that first bit, essentially. All right, so we can choose some value. Let's choose something like that. There's no sample and hold circuit on this because I made it in Altia, or whatever this is, Falstad, but you would need one typically. So I'll turn it on. And here we're going to make a decision. You can see the search. This is only 4 bits. So we searched here. We went to that high bit. It was too high, too low, and then we got to a value that's pretty darn close. And then you can see the binary value out here of what equivalent digital value is for that analog input. See, I know I'm not that great a teacher. There's somebody here who's got a question. Yes?
The sampling time is the time, the sampling.
Yeah.
Is the time to let the signal go to 0 to the analog value?
Yeah, the sampling time is, it doesn't always happen at 0. It's the time it takes to take the value in. So if we go, no, not DACs. Shoot. You're talking about this value here, yeah? Yeah, so this, you're not always coming from 0. There's no guarantee of that, but it's the time it takes for probably the worst case time to go from some value to something that's stable, to charge up that capacitor and then hold it. Yep, and then this would be the holding time for the sample and hold circuit. So you're holding here while you're doing the conversion. So you imagine if you have a high frequency signal or a time varying signal, you don't want it changing here while you're trying to do your binary conversion. That's not going to work out for you.
How do you know when the sampling time is over? Stable
You generally what you do is you however many bits your ADC is. So in this case, it's a 4-bit. You just run through 4 clock cycles through all the bits conversions, and your controller will just keep choosing the same value over and over and over again, or maybe it could oscillate between the last 2 bits depending on how it's set up. Does that make sense? So there's not a big value to creating a thing that says, okay, you're within a certain threshold, let's just stop conversion, because you don't know when that's going to happen. So from a system level, it's not like you're going to choose to take an ADC read faster again. It wouldn't give you much advantage. Does that make sense?
So like when the binary value starts to like, I don't know, like big small
Yeah.
changes, that's when you know that, yeah, we should start converting.
The hardware makes no decision to stop converting because there's no advantage to doing it. You could do that. You could totally make circuits and algorithms that say, aha, as soon as you converge on an answer, stop the ADC read and then send an interrupt and alert the core to come and grab the value. You could totally do that. But because you don't know what the input analog voltage is, you may save a few clock cycles here or may not save them later on. So now it becomes an undeterministic amount of time that you're saving. And that's just usually not that valuable in an embedded system. So saving those, going from 8 clock cycles to 16 clock cycles, not that big a deal. Does that make sense? Okay. What other questions do you have? They're talking about it right now. They have questions. They're not asking. Yes?
How accurate?
That's a good question. So you can get down The limiting factor is essentially the accuracy of your DAC. And again, we haven't introduced that. It's just a digital to analog converter. You put a binary value in, and an analog value comes out. So you can only be as precise as your DAC. And so a couple of minutes, we'll talk about digital analog converters, but those are essentially have the same limitations that all the ADCs do. You have some physical structure which is giving you your resolution. Yeah, and then the DAC, the input to the DAC, however many bits that is how long it takes to converge to your value, or the worst case conversion time. What are some advantages of this topology compared to the other two ADCs that we've looked at so far? Yep, that's true. Yep.
Was it programmable, like from software?
You can't, as a programmer, are not going to be able to program it, but in like RTL, which is, I don't even know what it stands for, real-time programming language or whatever, from a Verilog level, you can program that controller. What about speed compared to the other two ADCs? Yeah. So we know it's not going to, so flash is one cycle, right? So we're not going to be as fast as that, but a slope integrator is linear in time, right? You have to go all the way through every single bit value to get to the answer. So worst case, it's however much your resolution is. Here, it's 2 to the n, or n to the 2, to the n, oops. So you're much faster, but you have to give up some size because that ADC is probably going to be large. The rest of the components aren't that big. The DAC is probably going to be the largest part. The comparator consumes energy, but there's only one of them, which is nice. The digital logic here is actually on chip is going to be pretty darn small. It's going to be much smaller than, probably smaller than the comparator itself. And the timer that's associated with it is going to be built into the digital logic. So the size things are really the DAC and maybe the comparator a little bit. All right, any other questions on ADCs in general? Okay, so let's think about the pros and cons of each one of these. It's good to make trade-offs. Again, typically what's going to happen is you're going to choose to purchase a microcontroller. Like if you're an engineer out there, you're going to have a whole bunch of different parameters. How big is your program? How much storage does it need? How fast does it have to go? How many I/O pins? What peripherals you need? And you're actually probably not going to have that much control over the type of ADC on your device. Basically, most microcontroller manufacturers are just going to do a SAR ADC. It's a good trade-off between things. There are other types. Oftentimes, they don't even tell you what it is. But it only really comes into contention is if you want to buy an external one. You want an ADC that doesn't meet the goals of your microcontroller, or you could be something like you want to use a Raspberry Pi with an ADC, but Raspberry Pis don't have microcontrollers, so you're going to go and get an external ADC to work with your Pi. Maybe your platform just doesn't have it. Why don't you guys take 30 seconds or a minute to talk amongst yourself and figure out what you think these categories are for Flash, and we'll come back and talk about them, and then we'll do it for each one of those. So take a minute. And I guess these categories are like high, low, medium, right?
think it's just like,
I think the it's pretty complex.
All right, what do you think?
Oh, I had a question. What's the difference between accuracy and resolution?
Well, that's a good question. What do I think is the difference between accuracy and resolution? So I guess accuracy, you could state, is given the structure, what are the nonlinearities or the things that will creep into the structure that will cause problems? So you could have high resolution but still be inaccurate in the sense that maybe your system inherently has some noise source or some nonlinearities. That's what we mean by accuracy. I don't know, so what do you think for flash? And related to the rest of them, how do you think the resolution is? Yeah, pretty low. That's okay. How about speed? Okay. How about accuracy? It might be hard to actually say like good of a value, but what do you think would be the factors for accuracy for a flash ADC? Yeah. Is anybody? Yeah. I think we'll call that resolution. And so you could have something that's really high resolution, but is inherently inaccurate. Those two things can be true. We'll talk about, you'll find out in just a second why that is. Any other thoughts about why it would be, what would lead to poor accuracy? Yeah.
Bad comparators.
Bad comparators, yeah. So if we think about process variation on your chip, if those resistors were not made exactly the same size, then you're going to have an unknown voltage differences between those nodes. And so how does that happen? Well, as you make your resistors, the fabrication process does not inherently make things exactly the same. One step is you actually go and polish the die while you go and put the next layer on, and that will unevenly take off some of the resistor metal or the poly resistor, whatever it is, on the edges of the resistor bank, and those resistors will have slightly different resistances. Not that you should remember that, and just know that just because you put a resistor down doesn't mean you get out the value, and there's some inherent reasons why it might be not great. But in this case, it's pretty good. You know, I marked it as good. Complexity, what do you guys think? Yeah, I said it was pretty simple. How about power? High. Why is power high? Yeah, the resistor ladder is not that bad. It's not, if you had to have it one resistor to ground for each one, those current draws to ground start adding up. But like just one resistor ladder, okay. But it's all those comparators have to make a decision every time. They're always on and they're always flipping between ones and zeros to make a decision. So that's challenging. What about cost in terms of die area? High. Yep. All right. Why don't you take a couple, that's what I put down. Why don't you take 30 seconds, talk to your neighbor about slope integrators and how they compare to flash.
I'd say the speed is definitely worse.
power would be better because as a voltage point, base resolution depends on the size of the I guess it's a register. But I think with more power, with the power, like extra you only have 3 resolution, you can say it's so there's only one
Okay, what do you think? What do we think for resolution for slope integrators? Yeah. Very good, yep. Somebody's can look ahead in this. Oh no, I didn't actually write that, but yes, it is high. It is good. How about speed? Slow. What about accuracy? You're not going to know exactly the answer. We're not an analog circuit design class. What's your intuition say?
Better.
Yeah, I would say it's probably better. You're not trying to make a comparison between two different resistor values, right? Is really just measuring time. So that should be pretty good. Complexity? Yeah, medium, maybe a little bit higher than a flash. Yeah, I don't know. It depends how hard you think it is. The complexity of making a nice current source in analog is. It's not that bad. Power consumption. It's got one comparator. That's nice compared to flash ADC, which has lots. How about cost? I'd say it's low. Yeah, it doesn't take up much space. All right, take a couple 30 seconds or so to talk about SARs.
I think I would say resolution. I guess it's the same thing as high it's just like you're never going to get it depends on how you're going to I think there's more place for error with like EDAs. It's a whole thing on itself. Yeah, it's like how complexity. That really. This one's like much more complex. It's
All right. What do we think about SAR? How's the resolution compared to the others? Medium? Okay, that's about right. I think so. Speed? Medium? I think I said resolution is medium to high. I don't know why I said that. You'll see in a moment, but it's certainly not as high as slope, but it can get pretty high, right? It's as good as your DAC is going to get. Accuracy? What do you think? We haven't talked about DACs yet, so you don't know. You don't know how bad that's going to be. That's a trick question. I said medium. How about complexity? Yeah, it's high. There's a lot of little things to get right. The nice thing is that the search algorithm and the control algorithm is all in digital. So you're not going to get corrupted by a bunch of analog stuff in there. That should at least work, but yes, it's much more complicated. Power? Medium? Yeah, I think so. Right, there's a missing part you don't know about DACs yet, but it's not going to be, we already saw it has one comparator in it, so that should give us a hint that it's lower in power consumption. And it will, I gave you the hint, it will probably have less resistors than a flash ADC at least. So yeah, it should be lower or medium in power. I guess I just gave away cost. So if it has less resistors than a flash ADC or the equivalent of a flash DAC, then it's going to be somewhere in here. So I said medium for power consumption, or sorry, for area. Good trade-off between cost and speed. Okay. Any questions about trade-offs in this table? All right, so on your STM32, you have a SAR ADC. It's a pretty nice one, actually. STM think about it as IP modules that they can go and take and put on different microcontrollers. And the L family has the nice set of analog peripherals in it, and some, like the value change does not have as good devices. So this is a 12-bit ADC that goes at 5.3 megasamples per second. So that's pretty fast. Like that's in range of like really, like maybe not an oscilloscope. Oscilloscope kind of averages 100 megasamples per second, or sorry, like a starter oscilloscope's like 100 megasamples per second, but for $3, you're pretty close. Like that's, I think that's pretty great. Because it's a SAR, I should have said this, you can deterministically choose to lower the number of bits, stop converting early, and then go faster. Now, you don't get any advantage from, saying it either go between 6 bits or 16 bits or 12 bits or whatever, like just give me when it converges stop, but you can choose to have it stop earlier, giving you less resolution, but much faster speed. So you could go up to 8.8 megasamples per second at 6 bits. It's pretty interesting. You get 16 external channels, which means there's 16 ways to get the signals into your DAC. There's only one DAC, or there's only one ADC, but there's 16 different pathways to get it into, or different pins that can be ADCs. Then you'd have to time multiplex between them. We talked a lot about the internal, or those references when making that ladder that converges between analog voltages to binary values. There's that kind of step ladder that's in there, or staircase. And the bottom and top of that is the reference voltages. So you have internal reference voltages. You have 5 different channels for that. So you can use power, you can use VDD, you can use ground. There's an internal voltage reference, which I think is like 2.2 or 2.8 volts. The nice thing about using that internal is it's very quiet. It's all generated on chip with something called a band gap generator. So basically, it's a reference voltage that's not going to be corrupted by the power supply. And if you're out there switching SPI or UART, you're pushing lots of current through transistors. Where does that current come from? That current comes from your power supply. So all of a sudden, you have all these voltage spikes or current spikes on your power supply. And just you can't get rid of them. And now that's going to corrupt your ADC measurements. For what you guys are doing, probably doesn't matter. Nobody cares. Maybe you're just fine. But you get out there in a world where you're trying to make really accurate ADC measurements, you either cannot be doing ADC while you're doing SPI transactions, because you'll actually see the noise from your SPI on your ADC values, or you have to use a different reference voltage. There's an internal temperature sensor, which will be read by the SAR ADC. Almost every piece of silicon gets a free temperature sensor. It's great. If you take, there's a trick where you take, let's see, what would you do? You take 2 identical diodes and put 2 different currents between them. You'd have to know what those current values are, and that the voltage difference across those 2 diodes is proportional to absolute 0. It's like within half a degree or so accuracy. So almost any silicon device, if they have an ADC, some way to take that analog voltage difference between the diodes and turn it into digital, will give you a temperature sensor for free. You can also look at your battery power. I think this has an internal buck or something, I forget. And then you can also feed it DAC inputs if you wanted to. Kind of why would you want to do that? At least you could calibrate your DAC. Maybe your DAC is acting weird. You can put your DAC back and feed it, loop it back into your ADC. Kind of weird, but possible. You can do 16 bits with hardware oversampling, so it gives you the option. You can sample multiple times and get higher resolution, so we'll do averaging for you. That's buried in the data sheet. I think it's a cool feature that you can, in software, essentially in hardware, but as a software method, not a direct ADC measurement, you can upsample or oversample your values to get higher resolution. This is also cool. I haven't seen anybody use it. But you can have analog watchdogs. So watchdog timer, we talked about timers, was a timer you set up, and if software doesn't go back and reset the timer before it expires, it will reset your chip. Why would we want that? Why would that be a good thing? Sure. That was fine.
Well, if it goes into a bad state, you want to be able to reset it so you don't go back to stable.
Yeah. So watchdog is something in the idea that it watches something for you. In that particular case, it's ensuring that you're getting forward program execution. For an analog watchdog, you can just say, hey, if something goes over a particular value, maybe you're just looking at a light sensor or something. You want to know if the light's turned on in the room. We don't want to always have to do ADC conversions, right? You don't want to have to write the software. You can just go and say, hey, go watch this pin for me and throw me an interrupt if this thing goes high or over a certain value. Yeah.
Are the DACs, like, in the chip, different than the ones that the ADC uses?
Yes. Yeah. They don't. It's much easier from a design point of view just to take a DAC and make it specifically for an ADC rather than trying to time multiplex the usage when you're trying to access it and send out analog values and then have it choose something internally.
Okay.
So, yeah, that's a good question. It's all just wrapped in that SAR ADC box. You get to also change your conversion time. You have prescalers and different ways of converting the time. You can increase some accuracy in this way by changing the conversion time. I don't think it really matters for this class, but you can see some of the trade-offs in the data sheet. This is just an example here. So here we're talking about you have your sampling time, you have your conversion time, so you could go through and figure out with a 16-bit clock or 16 megahertz clock, 4-bit sampling, and do the math to figure out how long will it take you with these two combined steps to do an ADC conversion. Then so that you can figure out how fast you're going to be able to run your SAR ADC to see what's the fastest sampling time you're able to get. There's also a point where you have to convert and you actually still have to get the data out of the SAR ADC and put it somewhere. That can have some overhead. There's a mechanism called DMA, so DMA, Digital Memory Access Controller, something like that. Basically, it's a tiny little core that only does very simple things. It just takes data from one location and puts it in another location. So oftentimes what you end up doing, if you want to go as fast as this hardware can go, is you also set up your DMA controller. When an interrupt goes off, it grabs a value, sticks it into memory. That way your core doesn't have to do that. The DMA will set up basically a path through the APB bus. In this case, I think it's on the high performance bus. It might be on the peripheral bus. In any case, it'll set up in its own basically pipeline to take the data and stick it into memory. You get to choose data alignment. This is maybe just for your information, not a critical part of understanding ADCs, but just to know what your thing is capable. So you can define where do you want the bits in your, when they're put in the output register of the ADC, how do you want those bits to be? And that just helps you when you're trying to pack bits as tightly as possible into memory later on. Let's see. So there's regular versus memory, or regular channels versus injected channels. Injected channels just give you the option of automatically switching between multiple output or input pins. So it's an opportunity where you can just say, okay, I want these 4 input pins. I want you to go through them as quickly as possible and wrap around and continue. And so you will get an output register. Basically, you can set your thing up to sample effectively as fast as possible in kind of a round robin modality if you choose the injection channels, or you just have a regular channel which just takes an ADC read, stops, and takes another ADC read. Just automating some of the pin reassignment tasks. All right. Yeah, that's basically the same thing. There's injection channels, there's cycling versus non-cycling modes. Okay. Lastly, I think this is kind of to wrap up. Well, there's a lot of it. It's not exactly what I think is important to teach anymore. Well, I did already say this. So knowing where these VREFs come from, where the internal ref come and how it's going to change this value. This scale is important. In your world, most of the things are going to be from 0 to 3.3 instead of 5, because that's the reference, or that's the power supply voltage for your ADC. But it may need to be, 2.8 or whatever the reference voltage is. All right. Just like all the rest of the peripherals, you can set up interrupts and timers. So you can have a timer going off that sets an interrupt up that will take ADC reads so that the timing is done for you. You want to sample at some determinate time for a number of samples. You can use your timers to do that for you, triggering ADC reads. When the ADC reads up, then you're going to go and grab that value, put it into memory. So a lot of that functions by concatenating the modules that you've learned in the class already can be added together to automate tasks so you don't have to do it in software. Yeah. Okay, so to recap, the things that I think are important to understand for this class. And this is more for your projects. For this class, you should know for ADCs, the 3 types of ADCs we talked about and what their inherent trade-offs are. You should be able to work through essentially how they work and be able to describe how they work. You don't need to be an ADC designer. And you need to know more or less when to choose one versus another one. This is more for your projects, kind of giving you a little bit deeper dive on what are the options and the things that are available for you for your projects. All right, any questions before we go to DACs?
Continuous for single shot.
Continuous is just that you're going to continuously set up the hardware through timers and interrupts to take a measurement and then retake a measurement and then retake a measurement, and then you're going to have to do something with that data. Right? And so that's interrupt's going to go off, and in your interrupt service handler, you got to go put it in memory, or you use DMA to put it into memory.
And single shot.
It's just to take one single measurement and tell me when it's done, and don't start another measurement.
So it can only take one measurement ever?
No, at a time. And then you need some software intervention to say take another measurement.
Okay.
So does that make sense?
Yeah.
Yeah.
Can you explain the ADC conversion time, like, so it'll be confusing? I guess how the values of the slides.
Okay, good question. So it tells you that the sampling time is 4 cycles. It's given to you. You don't get a lot of control over that. Your data sheet's going to tell you what your sampling time is for that. So that's kind of a fixed value. It doesn't matter how long you converge for, you're always going to have to pay this time penalty. Okay? And then it says that you have a 16 megahertz clock. And how many bits is the ADC? 12-bit ADC. So you have, in this particular case, you're going to have to do 12 successive approximations, right? You're going to have to go through this 12-bit binary search to find the value, okay? And so then you're going to do 12 clock periods of 16 megahertz. And so here's 4 clock periods of 16 megahertz plus 12. How's that? Does that jive with what you're seeing here, what you're thinking?
Yeah, I'm just like, how you got that time.
This time?
Yeah.
I guess we'd have to go through, well, I guess I could go through the math. Maybe the math is wrong, but I'm going to assume that this over 1, no, that shouldn't be that. 10 cycles plus that. I have no idea how I got that. Somebody want to do the math quickly, and tell me what it should be?
You have the clock speed up there. And
Yeah.
you know what the duration
Oh, clock speed, yes.
And you multiply that by 10.
Yeah. For a second, I thought that was, I misread that, misunderstood what that was. Does that make sense? So really, it's figure out how many clock cycles it takes, right? When you figure out that clock cycles, then you know what your clock speed is, then you can figure out what your conversion time is. And then this is just showing you the trick that you go, because it's a SAR ADC, you can choose to converge faster, converge early. There's no advantage. You do all the conversions when you set it up that way early. So you could do it at 6, and then you're able to run the whole thing faster. Yeah?
You're doing a 12-bit binary search, say, and you're spot on
Yep.
finding the analog value after 63.
Yeah.
Does it just return immediately, or does
It keeps waiting.
So it just
You set it up for 12 bits, it's going to go the whole 12 bits, the time it takes to do 12 bits. Because I think the challenge is there's no inherent advantage of stopping early, because then what do? Then you take another sample, and then your sampling time is all skewed, right? Your sampling, when you take a sample, is dependent on the analog voltage that just came in. And so now your time base is varying. Does that make sense?
yeah, so it just won't change the value.
Yeah.
It'll stay constant.
Yeah, it'll just wait till the end, and then it'll say, I've converged, take the value, the ADC, the digital value, put it in the output register, and start again if you've told it to do that. What other questions do you have? Those are good questions. All right, we'll go on to the fantastic and exciting world of DACs. So basically, we're not doing UARTs. We're doing DACs. Great resources if you want them. I think the big thing to think about here is DACs are simply they're certainly the conceptual opposite of ADCs, right? You're going to take some digital value in and turn it into some analog value out. But we're going to use some of the same tricks that we used from ADCs and reuse them to make DACs. Again, the function here, the goal is, you could use them for plain audio. Now, when you have an audio module, it's a very highly optimized DAC. It's optimized for a purpose of only giving 22 kilohertz out sampling frequency. They're going to do lots of smoothing because they know what the data should look like. It's going to be something that looks like audio. So you can think of all audio outputs as highly customized DACs for audio playback, or you just think about it as a function generator that you would use in lab. In most of the examples here, we're not going to talk too much about time-varying signals. So while it's true that you can change these values to make a sinusoid, it's probably easier to conceptually think about these things as just putting out an analog voltage for now. And then you could do multiple DAC outputs to create a sine wave. And then the DAC, the construction of that ladder that we did of, where you had voltages here and binary values here, you just flip that for your DAC where you have some binary values which would play up to some analog voltage out. And that's essentially what these equations are just implying through mathematics, showing that there's a conversion value. If you put some binary digital value in, and you know the number of bits of your DAC, plus your reference, you have to know what the conversion is from, what the high end, in this case, the positive reference voltage, it's assuming 0 in this equation, it'll tell you what the analog output is. All right, so we'll talk about the simplest possible DAC. And that is just a low-pass filter, right? If you want to go make really horrible sounds for your projects and you want to add the least amount of complexity, this is a way to do it. You could just take a pulse width modulated waveform, run it through a low-pass filter, and there will be some analog voltage that comes out. It's going to take away all the high-frequency switching that you see and give you some distorted sawtooth value. In this case, we've modulated. You can see the pulse width modulation is going from basically full 100% duty cycle or close to it to 0% duty cycle. So in here, you can see that the duty cycle is varying as a function of time. And if you low pass filter that, you're going to get this value out that will vary as a function of time. It's a super simple circuit. It's maybe a little easier to think about it in an analog, or sorry, at DC where it's just one value is getting filtered out. One of the challenges here is, we'll show in a minute, is if you put a big load on this thing, because you have a RC filter in here, you need some buffer to filter that out. So in your, I guess it would be weird to have a DAC module exactly like this, but in your projects, you might just need a voltage follower on the output just to buffer the current over here so your load doesn't corrupt your analog value. No, I don't have this one. Okay. So here is some pulse width modulation. I can change the duty cycle. You can see on the bottom of the screen here, I made it close to 100% duty cycle. We have some filtering node, and then I've just buffered the output. And so as you see, as I change the duty cycle, this analog value goes down and down and down. If I get to 0% duty cycle, eventually it will discharge down to 0. And I can go all the way up. Mm-hmm.
Can you explain what the amplifier does?
Sure, I can show you what the amplifier does. These are great questions. All right, so we got an amplifier here. I put this over here, and I'm gonna play, let's see, what is it, R. Drop this here, and then G for ground. Put that there. All right, so now I'm gonna put this here. Uh-oh, I didn't plot the right thing. View and scope. All right, so now we're back to where we were a second ago, more or less, right? I've changed the circuit around. If I move this, I don't want to see current. Well, you can see the current on there, but if I have that low duty cycle, the value is low, and I put it up to here, the cycle is high, right? Great. Made a great ADC, and maybe you want to have really good voltage control. I don't know why. Maybe your project just requires you have to have good voltage control. All of a sudden, I'm going to connect this resistor here. What's going to happen? I know, you guys are like, this is a computer science class. I don't like this. This is analog. You're a bad professor.
Is this going to act like a pull-down resistor and your voltage is always going to be low?
Yeah. We can increase the duty cycle. Let's make this thing even a little bit larger just so it doesn't pull down as hard. Okay, so now we got some current draw. We can actually see, if I increase the simulation speed, no, current speed. You can see that this is pulling some current out of the circuit, and now my value is corrupted low, right? So your load is too high for your source to support. You're browning out your output. But if I take it off, the thing will snap back up. Oh, I made this too light in this case here. I'll put it back. Let's try 5 as a happy medium. Okay, so off, it looks like that. I put that on. You can see it gets pulled down a little bit. It's lower here. I'm not going to mess with current right now. So does that, you asked that question. Does that make sense? All right, and then we'll change it back around, and we'll go put the buffer on there, and put this over here, slide that back there, and remove scope. Great. Now we're back to the other condition, the original condition, and I can change this around. Now I go put this guy on, let's say here. Doesn't matter. It doesn't make any difference to it whether this load is on or, oops. Oh no. Doesn't make any difference whether this thing is on or off, right? Now it's not connected to ground. It doesn't matter because the op amp is supplying as much current as the load requires, and all its job is to take the output voltage at the filter and reproduce it on the output of the op amp.
So does it just like scale it more?
Nope, doesn't scale it. This is a voltage follower. Sometimes we call them a buffer. So whatever the voltage here is, it's going to faithfully reproduce over there, okay? And that's all this topology does. It just reproduces it. But it doesn't matter what the load is now. Here, remember, we put a load on this, it browns the thing out. It starts sucking too much current around here. This op amp, being an active device, will supply as much current as is required to keep that voltage there. So this is why, like, maybe for some weird reason you've seen this in action. Home speakers that you would have for your stereo are like 8 ohms, I believe, and car speakers are like 16 ohms because it's easier, or vice versa, I forget. And they're 2 different worlds. So if you take speakers from one place and put them on the other one, they sound different. It's because their impedance is different. I don't know why historically they've had different resistances, but that's a case where you might have seen it. I don't know. All right, so any questions about this type of DAC? Super simple DAC. What are some good things about this DAC? Yeah. Simple. Yeah, a capacitor, resistor, and a buffer can make this today. All right, you know PWMs, you can make a DAC. What are some of the bad things about this? Simple, okay. Well, what does that translate to? What's the downside?
Poor translation from digital to analog.
Yeah, I mean, we got some voltage variation here, right? It's not a nice constant. You want it to be constant. What would be one way to decrease the variation of this voltage? Yeah. Yeah, we could, let's see. Yep, exactly right. We could change this frequency. Let's set this to 10K. So that's a little bit more solid. But there's a trade-off here. Yep. You could also change the RC constants to maybe help out. Okay. Great. Any other questions? Yeah.
If we increase like the frequency of the BWM, will that require more power?
Yep. Yep. Every time you, change, every time you go from 1 to 0, essentially, you're taking some capacitor got filled or discharged. And so you can look at that voltage. Inside of the capacitance of that capacitor, parasitic capacitance can be picofarads, and you've just wasted that energy. You've lost it. So that's the main source of loss, that and heat in your integrated circuits. Okay. Let's go on. Let's look at other ones. All right, so another type of DAC. So this is the resistance voltage ladder. What does this remind us of? Flash, right? This is kind of the inverse of flash. We're going to go set up, we have a reference voltage up there, so say 3.3 volts to ground. We're going to go select this ladder here. We're going to make all these little reference voltages. So this is a fancy voltage divider. And then we're just going to say, okay, we're just going to pick which one of these switches we want to connect to the output. Right? That's also a very simple way to do it. Go to Falstad. And this, you don't even need any time series stuff for this. Here, we're just going to go put some values in here. So 111, and there's this kind of decoding network that decides which switch goes on here. So these are like single pole multi-throw switches. And so what's happened here? We have connected VDD through this switch network to there. And if I went and chose this one, then I have this value is through here, right? So basically you have some decoder, which is this switch structure, selecting one of these reference voltages and applying it on the output. Yeah?
You could have as many switches as like 2D and bits in decoder.
Yeah. So now you have a lot of switches you have to deal with, and switches are not trivial to make in silicon. Okay. Not bad, but they're not trivial. What other questions do you have? Yeah.
Wouldn't it take up a lot of space and still kind of easy?
Yeah, every binary value you want, you have to have a resistor for. So this is great for teaching examples. It's also very fast. You get the answer in 1 clock cycle, so that's good. But the ultimate utility of it is going to be low in the sense that you can't get a lot of bits out for the cost and space it's going to take. But it's fast. What's another problem on the output that we have to worry about? Do you want me to get a resistor out? I'll do it. If I put a resistor here, oh, you guys are making me do it. Let's see, I put this resistor here. Wait, why didn't it go down? You go down. Oh, it's 100 ohms? You should go down. Make me a liar. All right, 100 ohms then. What? There's no current flowing through this resistor. Why not? Oh, I didn't connect it to the low. Oh, stupid. Falstat's hard. Computers are hard. The actual node is there. Aha, I've corrupted that voltage. So here I'm going to unconnect it to ground. So now no current can flow here. It's back up to 5 volts. I'll put it back on here. Now there's a path to current, and I've corrupted the output. Yeah?
Couldn't you just put an amplifier there?
Yep. Go put that voltage follower on there. Take care of it. So the voltage follower on the output is much like the sample and hold circuit on the input of the ADC. That thing's job is to sample a little voltage and hold it so that it can be analyzed and without being corrupted. Here, you don't want your output to be corrupted, so you're going to go put some circuit, a little keeper, a little voltage follower to make sure you're able to drive the load. So both of them are trying to deal with this finickiness of the analog world.
What would cause, I guess, in real world application, this kind of disruption?
You go put a speaker on there, the little 16 ohm speaker on the output of your DAC, and it's going to brown it out. It cannot drive enough current to keep that voltage there. Right? And so that's why you often need a power amplifier. It's just a little IC, another IC that will amplify that thing to make sound. Okay, any other questions with this one? So the big takeaway, oh, no. So the big takeaway is you're going to put some binary value in here, and you're just going to switch one of these, or select one of these reference voltages, okay? And it's fast, but it's limited in the number of bits it can be. Power is probably not that big a deal. I'd have to think about it a little bit more. The switches are kind of painful to make. All right. So, you know, the question's kind of worded in a weird way, but basically, wouldn't it be nice if I didn't have to have one switch or one reference voltage for every value? How do I reduce the number of resistors I have? How do I reduce the number of switches? What are the circuit topologies that would allow that? And so, did you guys look at summing amplifiers in 215? Is that part of the curriculum here? He says yes. Some other person saying, oh my God, don't make me remember 215. Fantastic. Okay, so one trick you could do is you could have binary values represented V1, V2, V3 going through a resistor that turns it into a current. Now I have a current being pressed into this summing amplifier. The summing amplifier is going to sum these currents and give you a proportional voltage. Now, if you have different amounts of current, say R1, R2, and R3 there are different values, now you can go and create basically a binary table of different values of currents that will sum together, producing a voltage. So let's see what that looks like. Ooh, I made a simple one. Is that what I want? I don't know if I like that one. Oh, I guess that's what I got for you. Okay, let's look at it. It's kind of confusing as a time series thing, but I guess this is a good example of a summing amplifier. So here we have a analog signal, sine wave coming in. We have a square wave, and the summing amplifier takes those currents. It's not summing voltage, it sums currents and gives you the summation of those two outputs. And so while this is probably confusing because I didn't find the right circuit, it's just showing you how a summing amplifier works. So if we replace those with DC values, then you can imagine that instead of two oscillating signals, you'd have the summation of those two values, and then you just give yourself n branches and put binary values into them. This is not a summing amplifier. What's this one? That looks like a summing amplifier. Fantastic. I knew I got there. Okay. So here, let's run this one. So here we have different resistor values. They're going to produce different currents. Now, the analog value that's coming in here is just going to be 5 volts or 0 volts. So it's some binary value. So now I get to choose a binary value in here, and it's going to have different proportional currents to the resistor that's being dropped over. If you remember your painful op amps, for some odd reason, it's trying to drive the negative pin to 0. Now, don't know why, it's fine. Let's just accept that that happens. And so now it's 5 volts dropped across 100 ohms gives us some amount of current and some voltage out, and I'm going to add a little bit of current. So this is not a lot of voltage, not a lot of current through here, but I've added a volt. So now, in this particular case, it's giving you a negative output. Let's, for the sake of this class, assume that we can magically convert that into a positive output and everything will be fine later on. But you can see by how to choose these binary values, we can get a summation to give us a proportional output voltage. Yeah?
Convert like negative 15 volts into that map it to like the binary value.
Yeah. And obviously, internally, you don't have a negative voltage rail. They're not going to give you negative 15 volts or negative 3.3 volts out of your DAC on your chip is going to give you an actual voltage between 0 and 3.3 volts or whatever your rails are. So don't get concerned that this is a negative. It's just the easiest way to explain how the summing part works. I see confusion. I see terror. This is analog. So the things you have to take away. What do you have to actually learn about this one? There's a magical thing called a summing amplifier. It works in some way. Who knows? Doesn't matter. You have some binary values that come in that are selecting some amount of current that goes through. It's the value of those resistors, right? You're summing effectively the current that goes through a 100 ohm resistor. There's a lot. And the current that goes through 200, the 400, and the 800. And those are all different proportions. And so now I'm going to connect a lot of current, a little bit of current, a little bit of other current to make a binary value that comes, or the binary combination of those will give me a proportional analog output. So what would be one of the challenges from a manufacturing capability for this circuit? Yeah. It's true. You need at least a resistor for every bit. And you need one extra because of just the summing amplifier, but it's better than the what do we call it? The ladder version of the DAC. So we've improved in the number of switches we need essentially, and we've improved in the number of resistors we need. What other manufacturability things should we think about? Yeah.
A lot of different types of resistors.
Yes. Right. So now, if for some reason now you notice these are all powers of each other, right? So you can. So imagine you need a lot of different resistor values, and some of them might be slightly different due to manufacturing tolerances. So now you think you're giving out some amount of current here, but it's actually something different. If they're all the same resistor value, then they're all going to be skewed in the same way, right? With the ladder scenario, all those resistors were the same. So if they're all, you wanted a 1 kilohertz and they're all 900, 1 kilo ohm, and you actually got 900 ohms, it's okay. The proportional steps are all the same. Here, it might not be okay. So you're susceptible to more error in these sorts of things. The way to mitigate that is they'll basically take all the resistor values will essentially be powers of 2, and so you put 100 ohms here, and in your manufacturing, you stack 1, and then you put another 200, another 100, another 100, link them together. So when they are fabricated, they're as close as they can be. Yeah.
I was going to say also cost, because if you have different types of resistors, you have to order all of these different types of
Well, it's true, but we're in silicon land. So you're just fabricating them on chip. So we think about the area cost and the linearity cost more than we think about the purchasing cost, I guess. What's one advantage of this type? We talked about area compared to the ladder. Any other advantages? Yeah. Yeah, it's fast, which is great. We want it to be fast. Okay. Let's see. And then the last is a combination. It's the R2R ladder. It's basically a more interesting combination of, yeah, it is. It's more interesting. I don't think I got this one, though. Some modification allows you to, let's look here, get rid of that. All right, binary, oh no, this is not the binary, this is the R2R ladder? Yes, okay, great. So this one's a combination of adding resistors and switches. So now you have a current distribution network and you're able to switch which currents you want off of it. So let me see, oh, here we go here. So now you get a binary decision between, let's see, I'm gonna connect this one here, connect that one. What am I doing here? Oh, okay. What? I think this is essentially the same as the one we saw before, except a better switching mechanism. All right. Sorry for the distraction, not the most important one. We need to get to the binary weight in time. All right. So the binary weight is the most likely one you're going to see. Let's make sure I get this one. The goal of this one is trying to optimize the number of resistors that you get and the number of switches. It's still a summing amplifier topology, only you're summing the weight of these individual resistors, and they're all, again, in a proportional relationship to each other so that you, for manufacturability reasons, but it has switches to help you out. So you're actually putting in voltages instead of currents. Okay. Let's see how that works. That's the same one I saw before? No. They're all messed up this year. So what do I want you to learn then? If I mess it up, what do I want you to learn? Let's go through this. Let's just walk through this together then. And I'll make a summary slide or something on Piazza because I think those got messed up. But okay. So the PWM low-pass filter version is not really ever used in industry. I mean, maybe if you had some really cheap device, right? You're making kids' toys. Kids' toys are a great place to play as an engineer because you have to really hit the cost value structure. But so it's good if you just need a basic ADC. Resolution's pretty good. It's based on time, right? It does have accuracy issues because you got some time variation in there. Speed can be okay fast. The linearity, I would say, is okay. It's not great because it's based on this RC time constant. You imagine that you put some resistors and capacitors down, and you hope that those values are good, right? You hope that the manufacturer actually got them, but they might have some variation, and so what you'd normally have to do is calibrate that. You'd have to go through and actually measure the output value for some PWM. So that you can do that, you just don't want to do it in a production environment. Complexity is good. Power's okay, but the complexity is great. So the voltage divider method, or the voltage ladder, we talked about that one. That resolution is limited to area. You have to have a resistor for every binary value. It's fast. We would say that for integrated things, the linearity is superior to the rest because it's the same exact value for each one. It doesn't scale well, power's okay. And then we start thinking about the resistor counts and the switches counts. So switches, they're not bad, it's just they're a pain to make. They have to be biased, so there's some overhead for unintegrated circuit switches. So we say 2 to the end and 2 to the end switches for that. So that's a challenge for the number of resistors and switches you need. The R2R ladder has, let's see. So all these have, you're not going to have this infinite resolution, kind of like the slope integrator did. That is based fully on time, but it's better than the other ones. It's fast, fairly good linearity. These are even ratios of each other, but it doesn't scale well. This one has you get an extra resistor for that op amp, but you have less switches, which is nice. So that's the gain you get here. And then the binary weight, which I'll have to make a better slide on and go over it next time. It's nice because you're basically getting less resistors and less switches than the alternative. But linearity is going to depend because you have lots of different resistor values. So you gave up linearity for these other challenges, or for lower number of resistors and lower number of switches. So those are just trade-offs you have to make. Yeah. All right, so any questions on trade-offs? Yeah.
Can you explain what
Sure, so when you're trying to go, like, what's the variation from one binary value to another binary value? Let's go through, this is a reasonable size. This is a slightly different concept of differential linearity, but basically those steps, we assume they're going to be exactly the same size. but there could be manufacturing errors which cause them to be different. You as a user or a designer, the only way you could figure that out is if you go and calibrate every ADC or digital value and measure it out. And so that's probably impractical, especially if it's a high amount of ADCs, DAC binary values. And certainly couldn't do it in a production environment. That just wouldn't work out. So linearity is the amount of variation you get, and then the manufacturers of your ADCs are going to give you some metrics on what they guarantee their linearity to be based on their fabrication techniques in the device itself. What other questions do you have on trade-offs? All right. You have DACs on your STM32. 2 sets of DACs. You have 8 or 12-bit modes because, you have just gives you different options of how you're going to use it. You can synchronize them, so you could do like stereo, essentially, if you wanted. There's an interesting ability here to have what they consider a sample and hold, where say you want to, for power consumption reasons, you want to have an analog voltage out, but you don't want to have your DACs actually running all the time, like constantly outputting a voltage, right? You can actually put it in sample and hold mode, which will take the DAC output, put a buffer there, allow the entire microcontroller to go to sleep, and then it will just reproduce that that voltage from a buffer. So it'll hold the voltage on a capacitor and push it out of the pin and just hold it there while the entire microcontroller is asleep. So that's just a way to increase or decrease power consumption with this kind of inverted sample and hold, sample and output hold in a sense, rather than the other way we talked about it was sample and hold for the input signals. I want to talk a little bit about sources of error in our 4 minutes remaining, and then I'll let you go. We're not going to, we used to, especially this professor came before me, used to love to talk about all the types of error and have you quantify all the error. I think he had a research project on it. That's why I was really excited about it. I think for you guys, I want to give you some rules of thumb to understand where error comes from and why that might impact you later on. So we talked about quantization error. Just inherently, you have some analog value, so this would be for DACs or ADCs, but think about from the ADC point of view, you have some analog voltage that is coming in, you get a binary value out, but you have some uncertainty. You don't know what the actual analog value is. Or from a binary point of view, you want to put out a value, you want to put out some analog value here, but you just don't have the binary space to actually put it out. So there's some error in what you desired for an analog signal from what you can actually do. And that's just related to the quantization. And so here's this, an example of from half bit off to plus, well, this should be minus, plus or minus half a bit of error based on how you set up your DAC, ADC.
And could you minimize the quantization error if you increase the number of bits?
Yeah, totally. You just pay the penalty on having more bits, more complexity. So that's one way to get around that. You'll find things, some errors are easy to overcome. So offset error. The negative rails, or the rails, the positive negative rails may have some bias, or inherently internal circuit, it may offset the values from what you expect. So you put in some analog value here, and it's actually giving you this other analog value. That's easy to correct if you had a calibration step. So you can go through and measure a few DAC values or analog, or put a known analog voltage in, and then you could come up and say, oh, I'm consistently off in this error, and now this is just a software update to say I have a static DC offset. That's an easy error to fix. In the production world, you have to have some way to detect that without putting it on a test bench and measuring it for every device. There's other errors called full-scale error or gain error, which means that there's a consistent gain aspect, so that in this particular example, the higher the value is, the more error. If it's nice and linear, that's just an equation you have to apply to compensate for that amount of error. So all these three, this is just acceptable, like this is just your design, you just have to accept it. These are recoverable, you can measure them. But the ones that you can't really deal with is differential error or nonlinearity, where there's some aspect of your outputs that the spacing is not all the same. And the one this really comes up is when you're making a control loop and you're trying to have this digital value, say, you're trying to serve one analog value to some value, but the digital may overlap. There may be problems. You might do in a search space and you're actually getting caught at local minimum. That can actually happen because there's so many bits that there's little bits of error.